Okay, about the students, so now we start quick revision of the important topics that we studied throughout the material which is covered by your midterm exam one, which includes the introduction chapter as well as the graph theory chapter. So we start with one important concept that we have covered already in the material is a protocol, which is a set of steps or algorithm that defines how nodes communicate together. And one important aspect to understand about protocols is how to represent them using time sequence diagrams. So we should be able to represent a given protocol, whether you know it before or it's told to you in the exam. If you are informed how the protocol works, then you should be able to construct a time sequence diagram for that protocol, as well as constructing a flowchart. And we have done some of these already as part of your assignments and tutorials as well. So that's one important thing. Next is actually the concept of different delays that are experienced by packets being transmitted over the network. And the first one that we learned about is the packet transmission delay, which relies on or depends on the length of the packet as well as the rate of the transmission between the two communicating nodes. So the division of L over R, make sure you correctly use the units, make sure it's bits, right? And units of time is seconds so that you can get the correct packet transmission delay in the correct unit. Okay. Another important thing is when we are talking about sizes. So when we say the size of the packet is 1 kilobit, for example, then in this case we use the K is the kilo. In this case for binary is 1024, so it's 1024. So K kilo for size is 1024. However, when we are talking about speed as a convention, then kilo, for example, so here when we say kilobit, for example, okay? When we talk about speed or rate of transmission, so we are talking about kilobit per second, or it can be written as kilobit per second, okay? Then in this case, the kilo in the rates is just 1000, so it's 10 to the power 3. So when we are talking about kilo in size, something like when you are measuring the length, then you use 1024. When we are talking about kilo in transmission rate, it's just 1000. Okay. And again, the same applies for mega. So mega here becomes 1024 times 1024. Mega in this case, in the case of the rate, becomes 1000 times 1000, right? Which is 1 mega, and so on. Okay. That's a convention that we would use for our calculations in general. Okay. Remember, we studied two methodologies for switching, the circuit switching, the packet switching. We had several examples in how you can solve problems on circuit switching versus packet switching, so you can expect to be asked about something like that. In addition to that, we've also looked at the situation where in packet switching, if you encounter a transmission delay, then it's per link. So if the data is going from this node until this node, it has one transmission delay from here to here, and then another transmission delay from here to here. And if we have more connections, then a third and a fourth and so on. Each one of them might have a different rate. In this example, they have the same rate, but they might have different rates. Why? The transmission delay is accumulated. We mentioned that already previously, because in that case, the packet cannot be forwarded, cannot be resent unless it's completely received first from start to end, and then it will start the next transmission over the next node. So this is why the transmission delay is accumulated in this case. However, if we are talking about circuit switching, right, so the data goes through without being stored in the middle. So it will go through here. As soon as a bit is received here, it can be sent to the next one because there is no local processing. The whole path is preset at the start. It's not decided by packet. And in this case, the transmission delay does not accumulate because as soon as it is being transmitted here, it's also immediately being transmitted or forwarded to the next and so on. So in that case, you don't have accumulation of transmission delay. However, you can have accumulation of propagation delay because propagation delay has to do with traveling. So it's traveling here and then it will have also to travel this distance and so on. Okay, so keep that in mind as well. Transmission delay does not accumulate in case of circuit switching, but it does accumulate. So you have multiple transmission delays when you are dealing with packet switching, moving from one link to the next to the next. For circuit switching, it's the same. It's a fixed transmission delay, no matter how many links you go through, because you don't need to wait for the whole packet to be received and then forward it to the next link, right? You can just immediately forward it bit by bit as soon as they arrive. However, the propagation delay has to do with the overall travel distance. So keep that in mind. That's a very important one. Okay? Another type of delay that we have discussed, but we did not say how you can calculate that, is the queuing delay. Queuing delay, we explained that as well. It's another type of delay that has to do with the buffering of the packet at the intermediate nodes. So that typically queuing delay happens also in packet switching, doesn't happen in circuit switching. And the important things that we mentioned also is the operation of routing, which is finding the path, and the operation is forwarding, just moving, which we called later switching in the new material, which is simply deciding which way the packet should go. And then here is just another re-emphasis on problems that you can solve on circuit switching and packet switching. Remember that for circuit switching, the resources are reserved throughout the whole transmission. This is not the case for packet switching. It's packet per packet path and packet per packet resource reserved. This re-emphasizes the packet switching mechanism. And again, we have several problems on those. Remind you that you need to be able to solve those problems. Another thing that we discussed also is that not only delay is the issue with transmission, there is also the issue of being exposed to packet losses. This may happen if your memory or your buffers gets actually filled. Again, this can happen in packet switching. And in this case, you might lose some of the information and the measure of loss. So in addition to something called delay, which includes 4 components, we have already mentioned 2 of them, the transmission delay and the queuing delay. There are 2 other delays we mentioned in a couple of slides coming later. But we also have something called packet loss, which can happen in packet switching. And the measure of that is either something called the probability of loss, how many packets, like the total number of transmitted packets you on average you lose, or something called the throughput. Okay? Going back to delays, we have 4 types, right? For an overall packet transmission system. So there is something called processing delay, which is the time that a particular node spends to understand the information of the packet. That depends on the processing speed. Like if it has a processor that can handle 5 packets per second, then the packet processing delay is 1/5 seconds, right? Then the queuing delay, how long the packet stays in the buffer before being transmitted. Then the transmission delay, how long it takes to transmit the packet. And last but not least, the propagation delay. Again, you should be able to calculate all of these given information in the problem and solve the example related to those. Here the expressions are given. This talks about the queuing delay. So sometimes, even though you cannot calculate the queuing delay, it can either be given to you or you might be given some graph that tells you for a particular load, which is measured by something called the traffic intensity, which is L, the packet length. multiplied by A, or sometimes we call that lambda, the average packet arrival rate, divided by the transmission rate. For a particular value of this parameter, you can use this graph to figure out what's the queuing delay, right? So if you are given such a graph and you have L, A, and R, you can actually use the graph to figure out what's the queuing delay. Okay, so keep that in mind. That might happen. Okay, that's for the and again in real time. Keep in mind that it's not just one node talking to another. It might be multiple hops between the source and the destination. So you need to be able, given a particular problem, to calculate the overall, for example, propagation delay, overall transmission delay, overall queuing delay, overall processing delay. And in the case of packet switching, all of these are going to be accumulative. So you calculate for each link and you add those numbers together for all the 4 parameters: propagation, processing, queuing, and transmission delay. If it is a circuit switch system, then you don't have processing, you don't have queuing, you only have propagation and transmission. Propagation is going to be added, just the different things, you add the value. Transmission delay is only one transmission delay, which is equal to the packet length divided by the rate of transmission. In case of series connection, your rate is going to be calculated using the lowest rate length. So among those different lengths, the one with the lowest rate is going to define how fast is the whole circuit. So in this case, you can think of this as one cable, and the rate over that cable is the rate of the smallest link. Okay. Going back to packet loss, just want to remind that when you are dealing with a system with multiple links and you have some input arrival rate, you have speed for link 1, speed for link 2, the throughput across this is the lowest among all of those. So you look at the rate of the speed of first link, the speed of the second link, and the arrival rate, right? And the smallest of all these 3 is the one that defines what's your throughput, what's your output from the system. So again, if you have arrival rate lambda, which is given in bits per second, everything has to be in the same unit, right? And you have a speed here, S or R1, speed of transmission, again in bits per second, and you have another transmission rate here, bits per second, right? Okay. Then your throughput is gonna be the minimum of all these. Lambda, R1, R2. Please notice that sometimes in some problems I can give you lambda in packets per second. In that case, you need to multiply that by the packet length so that you can get the arrival rate in bits per second. This is very important. Okay, that's just the elaboration that I mentioned. And one more thing to keep in mind is that if you have multiple rates or multiple connectivities going through some shared link, then when you are adding this link to each one of those paths, you have to keep in mind that the rate R here is shared somehow between the different links. So for this link, maybe it's equally shared. So for this link, the rate on this is going to be 1/3. For this whole circuit, the rate here is going to be another 1/3, and this is a third 1/3 of this overall R, because it's shared among them, right? It depends whether it's shared equally or shared within a given a certain ratio. Okay, so you have to keep that. Last thing is to remember the 5 internet stack layers, responding 7 ISO open system interconnect layers. Keep that in mind. It's an important concept, and that communication when it's taking place from one node to the other, it's one layer to one layer. So physical communicates to physical. If I use data link here, it's going to take to the data link here, and if I use the network here, it's going to take to the network here, and so on. So those layers allows you to abstract things and think as one layer different to the other without really caring about what happens above or below that layer. Even though in a full communication, the whole layer stack is being. This is it for the first part. I'm gonna now provide right after this another video review of the part on graph.